So we'll start with our use case. I mean, as we mentioned before, about a vulnerable road user crossing the street somewhere, being observed by camera, and somehow through a pipeline of services that can be located in any computational node, sending a warning at some point to a vehicle, or letting him know in advance of what he can detect himself. So we have that's the application layer, right? So we are going to talk below this we have a computation layer with multiple nodes where you can distribute the computation. And below that, interconnecting the nodes, you have many different wireless technologies. Well, some wired technologies too. And that's what we will be working on. And now, precisely in this first part, I'll be talking about these Wi-Fi links that exist to a large extent in our cities, but they exist in the cities, but they are currently not used for mobile nodes. But they could be, some of them have very high throughput and they could support cellular networks when there is low connectivity or the cellular networks are crowded. So we were measuring this. This was part of WP4. We developed YPerf. It's a tool to do two things. One hand, collect data, and also for testing decision-making in real time. So this has two functionalities. On the left, we have the mobile client. On the right, we have the access point. First, to collect data. In this case, we are sending data very heavily, making the channel busy. We are collecting data on the receiver side, as calculating throughput is just counting, annotating it with GPS, and then sending the feedback and collecting the data in this network performance database that you see here on the left. It's not highlighted. Then we have the second function, which is decision-making testing for network management. This is what you actually would do in real time. And in the real time, you will not be sending data at high, just for measuring the channel. So we have a channel monitor running, measuring both the data rates and several parameters that are being on the wireless channel. This data is being collected also on the same network performance database. So we have historic data and real or very short time data. And then, oh, sorry, this is in Portuguese. I didn't notice. Anyway, then we have the decision maker. We can actually then, from the collected data, do some estimation, prediction of what's going to happen, and then make the decision. So this is all. This blue part runs in real time, and what we are going to talk about next is about this throughput estimation. Okay. So now, first of all, with the red part of the previous tool, we collected two independent data sets in two totally different situations. One was in Gaia, the other was close to FEOP. One we were used for training a model, and the other was used to test the model. The devices were the same. Then we use a very specific kind of model. It's symbolic regression. The advantage of this model, it is interpretable and it is simple to implement on restricted devices because it's much smaller and much easier to compute than the classical, well, everything we know as machine learning. But this is trained in a slightly different manner. It's a meta-heuristic with genetic algorithms, which gives you a lot of solutions. It's just solution space exploration. And we choose the one that you see there in red. It is the one with a low expression, low complexity of the expression, and actually a quite high, a low estimation error. So a high quality of the regression. So just briefly, the results. This is the symbolic red line and yellow line. These are the things we developed. And you can see to the left is better. So this is a cumulative distribution function. To the left is better than to the right. On the x-axis, you have the estimation errors. And you see, we are actually always the best or the second best for 802.11n and 802.11ac. Throughputs for AC are already on the hundreds of megabit per second. So this is competitive with cellular networks nowadays. And this was a moving vehicle. Okay, for 802.11ad, which is the millimeter wave Wi-Fi, the performance, well, we're still among the best, but the performance is very bad in general. So you cannot really symbolic regression with the unscented Kalman filter has actually very good performance for real-time network management for a moving vehicle, for attaching to Wi-Fi. We have another work on this, which is done by Moshe. He's working on reinforcement learning to do a better decision on when to change access points, and that will be on the YouTube channel also for you to see. Just for millimeter wave, what we tried there was to try to not predict anything, but just try to do a position-based selection of the sectors. I hope that next week, I asked Danielle to do a video about this. So next week we'll have a video about this work also on the YouTube channel. So now this would be the topic on the physical layer. Now I'll be moving to something we did with Altis Labs, which is going back to our architecture there. We have these nodes on moving nodes, and we have the services somewhere in the edge. We've all been talking about this. And although the networks nowadays are not optimized for low latency, we still would like to know what kind of latencies can they provide. And what we did here is to perform active measurements again with a 5G client connecting to a 5G is a non-standalone, so it is a commercial network, and connecting then to a server running in a home device in the same city, just using also the commercial network for the wired access. So this is a over-the-top service, right? Not hosted at the mobile. What we did active measurements with a series of packet sizes and a series of interpacket times. I'm not going to go into those details. We just varied these so that we could then, when we observe something, sort of disambiguate if it's caused by the packet size or by the data rate or by the interpacket time. So like this, we have a series of parameters that allow us to sort of not stop at hypotheses that we cannot, reject afterwards. So we also took some care not to overload the channel before that. So how are we doing the measurements? One very important thing here is the synchronization among the two nodes, because we are doing one-way measurements. We are not doing back and forth and dividing by two, because for the kind of latencies we are talking about, tens of milliseconds, that is no longer the assumption that you have similar delays in both directions is no longer really valid. So we are measuring using LibPCAP at the network layer, and of course synchronization becomes a problem because we have to synchronize the two nodes. We try to do this using GPS. It doesn't work very well, even when the GPS is right outside the window, because the GPS, the poor GPS connectivity is giving you bad timings. So we had to throw away those data sets. We synchronize it with NTP. What you can see here on the left, you have NTP synchronization over 5G, on the right over wire, and it's a 1 order of magnitude, the synchronization error between the two. Okay, so NTP over 5G, because of the variations, probably on the wireless channels, whatever, we have still, both are sub-millisecond. Okay, so we can synchronize less than 1 millisecond, but they are still, it's much higher if you use 5G plus wire than if you use 2.5G. So these are the data sets we generated and shared with both Capgemini and Altis for some work that is coming up front. And I'm going to talk now, me and Andre is going to talk about this data set V2. So first of all, our measurements have no impact on the network traffic. You can see there's a very low rate of outliers on the measurements, and the packet losses are less than 0.0 something most of the time, actually. So second thing, we discovered this, which is an abnormal pattern. We would expect the delay to be a random, and this is not random at all. So we developed a method to detect this automatically, and we can detect that it happens mostly, or we observe this during nighttime. So these are periods of very low average delay. So we think that this happens all the time, but we only observe it when it is not masked by much higher delays caused by something else. So we looked into this to try to find out what this is happening, why this is happening. The reason we look deeper into this is that when we are talking about low latency, if there's something creating a non-random latency, we want to find out which element it is to deal with it. So it's a sawtooth pattern. We use a range and a period to characterize it. Two things. First, the range is always, remember we have a sub-millisecond precision, so this is 5 milliseconds of range. Then the range does not vary with packet size, interpacket time, or time of day of the measurements. This is what these images show. Then two other things, the period, so the length of this sawtooth, does not vary with packet size, but it increases linearly with the interpacket time. So now we are still looking into this. We have been able, so it looks that it's caused by some TDMA mechanism along the way. We know it's not caused by the 5G device we used. We know it's not caused by the GPON downlink. We are now exploring where it is the 5G. There's something on the 5G scheduling on the non-standalone or on the TDD or on whatever mechanism it is that may be causing this, because this may have an impact on standalone or not. We don't know as long as we do not find out.